Okay, welcome to the very last chapter of Chem 122. This is the transition metals and coordination chemistry. There's only 18 slides, you guys, so I'm going to try to rush and get through it in one part. Okay, the transition metals are the guys in the middle, the 3Ds, if you remember. Why? Well, what do they look at? They look at their color, if they're catalysts, if they're magnetic, what their biological roles are. Several of them are important micronutrients and their coordination compounds. In other words, when they bond to metals, or do they bond to molecules, or do they form ions, that kind of stuff. That's what they look at. Okay. A lot of your transition, chromium, cobalt, copper, iron, manganese, they're in, you'll find them in minerals. Okay. They're solid inorganic compounds. They call them minerals. You can see these on your food labels. Okay. Minerals are not named by common are their chemical names. They have, you can see their mineral name, chromite, cobalt, it's close to it, but not necessarily the same as the metal that they form. Most of the transition metals range from +1 to +4 as their oxidation. Some of them have multiple, which you remember copper, iron, those guys do. Okay. When we look at the metals, metallurgy is the science and technology of extracting metals basically from rock and then using them for whatever you want to use them for. Okay. So when you're doing this, first thing you got to do is you got to mine them. Then you got to concentrate that ore because there's a lot of other stuff in there. Okay. You got to reduce the ore to the free metal, and then you got to purify the metal. So that's your steps from when you mine it to when you finally get your metal at the end. Okay. Now, sometimes it's crazy because they purify the metal and then they mix it. Like if you have pure gold, you want to mix it with something else because pure gold is really soft. If you're making jewelry, you don't want 24 karat gold. You want 18 or so because it'll be too soft. And so they need to make alloys. So after they purify it, then sometimes they mix it with other metals. Okay. So the first row is the top column. Okay. That's the most common ones. That's where you get your iron, your copper, your zinc, the ones that people really know quite a bit about. Okay. 5 and 6 are very similar. So the first row is a little bit different than the last two rows, the 5th and the 6th. And again, we're talking in the middle, the D columns. Okay. When you look at their size, their atomic radius, as you go from left to right, they decrease. They get pulled in tighter, if you want to call it that. On the other hand, if you increase their nuclear charge, it tends to make them smaller. So again, you can see how it goes down and then up a little and then down. It's kind of weird how it zips around there, but that's how it works for their atomic radius. Okay, so the metallic bonds get weaker. They're usually weaker up here and over here, and then in the middle they're stronger. Okay, period 5 and 6 have about the same due to what they call the lanthanide contraction. You can't see it, I'm sorry, I'm covering it, but it's the effect of the 4f electrons on them. So when you get into the bigger ones, the f's kind of start messing around with the orbitals, and so they change their effective charge. Okay. One thing about transition metals is they tend to have a characteristic color. Okay. Part of the D sublevels is occupied, so you can end up with multiple oxidations. They can jump around. And then again, you get your colored compounds. And then some of them have magnetic properties. Okay. So you can see some of the colors there. That's when you mix them, when you make an aqueous solution, when you mix them with water. Okay. Again, the oxidation states, it can vary. The period 4 tends to have more. When the cations are formed, they lose their 4s electrons sometimes, except for the very first one, scandium. So they can form a +2 cation. From scandium to manganese, they can jump around again from the S to the D. The only one really in the first one that doesn't change much is zinc, which is at the very end. It's pretty much +2. But the other ones can have 1, 2, 2, 3. It varies. If they're magnetic, the electrons are spinning a certain way, and then the electrons possess a spin. And so what happens is when the electrons are spin paired, when they, if they're spinning one way, they get one with the other way, they cancel each other out. And that's called diamagnetic solid. Excuse me. So when you have an unpaired one, it doesn't have anybody to pair with, it's going to have a spin. Excuse me. So then what's going to happen is the adjacent atoms don't affect each other. So there's different types of magnetism. There's ferromagnetism, and that's going to be with iron. There's anti-ferromagnetism. So if they're magnetic and they're not iron. And then there's ferric, which is a different type of paramagnet. It happens at a much higher temperature. Okay, so here's ferromagnetism. In substances that have unpaired, you can see they're all spinning one way. The spin influences how they align, and therefore they have very strong attractions. They have very strong magnetic fields. Okay, these are permanent magnets. Okay, and you can see iron, cobalt, nickel, and some alloys will form this. So they're all spinning in one direction. Okay, you can see one's going up, one's going down. So what happens here is the have unpaired spins and an adjacent atom, so they kind of line up, so they cancel each other out. So they're not magnetic, okay? Because you can see the way they line up, they cancel each other's spin out. So examples of these guys would be chromium and then alloys. You can have iron alloys if you pair them up with the right thing, then they're not magnetic anymore. And then there's ferromagnetism. As you can see, they have spins that align opposite each other, but the spins aren't equal. So you probably have a bigger atom versus a smaller one. So you have a stronger spin in one direction than you do in the other. Okay. And this can occur because of different numbers of unpaired electrons, or because the sites align in one direction more than the other. Okay, so again, when you have stronger spins in one direction than the other, even though they're opposite if you look, that they're just not as strong. And so what happens is you end up getting, they're magnetized but not as strong. Okay, so the strongest one would be the first one. Okay, and then again, these are in alloys. Okay. So when you look at the charge of these guys, they're cations. In other words, they have a positive. They are going to give up their electrons. A lignan is a type. It can be an anion or a neutral molecule. They will form with some of your transition. And again, I'll show you some more in a minute. Their overall charge of the complex is simply the sum of all the parts. So like if I have iron and H2O3 with the H2O, this guy together has a +3 overall charge, so then you have to sit there and go, oh, let's see, iron's +3, there's 6 neutral waters. The water would be considered a lignan. It doesn't have a charge, so the iron must be +3. You can look at different ones too. Here in this one, the iron's +3 and the chlorine is -4. So those ions will act as lignans. Not a big thing, but just remember that irons are positive, okay? Here's chlorophylls. Chlorophylls come from magnesium. Excuse me. It's a key component in that it absorbs sunlight. Okay, it's part of photosynthesis. It's not involved in. It's like a catalyst. A catalyst, something that has to be there for the reaction to start rolling. That's what happens with chlorophylls. And again, they have a key component of magnesium. It converts solar energy into energy that we can use in photosynthesis. Okay. I'm not going to spend a lot of time on this. You guys know the nomenclature rules. When you have two nonmetals, you put them together. Well, if you have a lignite, it works the same. They have a system. We're not going to get too involved in that, but there's always a system and it tells you how many you have. Okay. And again, the complex ends in ATE or ITE. You can use Roman numerals. Remember, if it's iron 3, it's iron, and then Roman numeral 3. If it's iron 2, it's Roman numeral 2. That kind of stuff. There is isomers. Isomers is the same molecular formula, but a different arrangement of atoms. We haven't talked a lot about that. If you take an organic class, you'll talk a lot about that. But there's two main subgroupings of isomers. There's structural isomers that have the same molecular formula, but different connections. And then there's stereoisomers, where they have the same connections, but they're different 3D dimensions. In other words, stereoisomers are like mirror images of them. Okay, so you can move things around. Maybe the chlorine is attached to the second one, carbon instead of the first, or something like that. Okay, those are isomers. Okay, there's linkage isomers. Here's an example of a nitro isomer and a nitro. See, you can't see it, and I'm really sorry, you guys. But what happens is because they move around a little bit, you get, and it's just here on the bottom. See how it's linked a little bit different? Here it's linked on the blue, which would be carbon, and here it's linked on the hydrogen. And because that, you get different colors, you get different properties. Okay, nitrite versus nitrate. The colors, when you see the transition have lots of different colors, it's basically when light hits it, when white light hits it, it reflects certain colors of light and absorbs other ones. Okay, and the thing with transition is that that's a real common thing. On the top here, there's a mixture of violet and red, and the only thing that can really separate it into the colors would be like a spectrophotometer. Okay, if you're looking for complementary colors, I know you've probably heard of Roy G. Biv, but red is complementary color is green, yellow is complementary color is violet, orange is complementary color is blue. They're opposites of each other on the little wheel. Okay. Oh, I did it. Yay. I'm sorry I spoke so fast, you guys, but I just wanted to get done with that one because that's it. We are done. It'll be the same thing where last chapter you had some multiple choice questions. Got the same thing here. You don't have to do it, but I guarantee you will see it in the near future if you know what I mean. Okay? So anyway, we are now done with all of the material. Now it's just this test, unit test, and then your semester test. So long. I'm done making videos for you this semester.